Okay, you should be good to start this session, so enjoy.
Thank you, Kay. This is Dave Archer again, chairing session 3 on multi-party computation. In this session, we're very fortunate to have 3 interesting talks about secure MPC, and they include things such as the challenges encountered in building MPC products that have to deal with diverse environments, challenges in creating secure real-world MPC ceremonies, and the prototype maliciously secure MPC platform for federated analytics. Remember, each talk is 10 minutes in length, followed by 5 minutes for Q&A. I'll offer an audible 2-minute warning. If you'd like to ask a question of the presenter, please post your question in the Zulip channel for the session, as I won't be watching the chat channel in Zoom. In the interest of open discussion, please include your real name in the question, and please preface it with a question for speaker so that we don't accidentally read things or general discussion there. So with that, if you're ready, our first speaker is Yehuda Lindell, who's going to tell us about lessons learned and challenges overcome in deploying heavy MPC in diverse environments.
Hi, thank you very much. So this is joint work with Valerie Osheter and Samiran Lucci at Unbound Tech. So just for some background and context, Unbound provides key management and key protection solutions in software, enterprise security software that customers run. And it protects keys via MPC by splitting them between 2 or more machines so that to make it hard to steal them. The 2 product lines of relevance to what we'll discuss today are server-side protection, which functions like a virtual HSM, so you can split keys between a data center and a cloud or between clouds. This topology here is actually run by a real customer. And you can also have like a virtual smart card or token where you split keys between a mobile and a laptop and a server and run all operations in MPC. So the first important observation is that many companies offer or run a service. They offer a SaaS solution, software as a service, and when you do that, the customer has an API to access the service, and they don't really install anything, or maybe at most a small client. And what that means is that in this setting, the SaaS company runs its own software. They know what machines they're using, what network, what environment, what operating system. They have full control over the system. And in contrast, when you provide enterprise software solutions, then the customers run those. So you don't know what type of environment they're running in, what type of machines they're running in, what network they have. And the more you try to mandate that, the less relevant your solutions become. So if you require running on very powerful machines with very high bandwidth, then that's not going to be relevant for everyone. And if you are only willing to run on Windows, then an organization only using Linux machines will not buy from you. So this means that when we're deploying an MPC solution, we need something that is going to be relevant for everybody, and that actually makes it a challenge when using heavy MPC solutions. So nothing I say here is going to be extremely surprising, but I think they are interesting observations that help us think about what we need to do when we design these types of protocols. So the specific context I'll focus on is RSA key generation for malicious adversaries. It's a very complex protocol, MPC protocol, because of the difficulty of generating an RSA modulus where nobody knows the factorization. And this paper from Crypto 2018 had an impressive performance of 35 seconds on average for malicious parties when generating 2048-bit keys. 35 seconds may sound like a lot, but it's actually, for this type of operation, it's a very, very good time. And the experimentation was run on machines in Azure, Xeon machines, 64 gigabytes RAM, 40 gigabit per second network. That's actually quite standard. It's a strong machine, but not an extremely powerful or unusual machine. And these machines have 20 cores. And that was what the experimentation was done for this paper. The first issue that arises when you want to actually deploy this is that these machines are actually very expensive. And if you think about a deployment for a large enterprise, you want these virtual HSMs, for example, to be in 3 different regions. And each region, you want 2 pairs of machines for high availability. So now you need 12 machines across the world. This can cost, for these types of machines, between $50,000 and $100,000 a year. And so if you're mandating that they're the types of machines you need to run this solution, you're adding between 50 to 100K to the total cost of ownership of the solution. And that actually is not very desirable, especially when everything else in the system doesn't require such a powerful machine. So this is already an issue just straight away with the cost of these more powerful machines. The second thing is that I want to relate to is multi-threading, and it might seem, what's the issue? All computers now are multi-core computers, and we can run everything multi-threaded. There's no real issue. And so maybe we should detect the number of cores and parallelize to that number, or just use many threads. And if we're not using some tens, it's not going to be too much of a penalty. The problem is, and again, we're running this solution in the context of something that the customer is using. So when we think about MPC protocols, we think, okay, I want to do RSA key generation. But that's not what a customer wants to do. A customer wants a virtual HSM solution that does RSA key generation while doing database decryption operations, code signing, authenticating users, and doing whatever else it needs to do, whatever other cryptographic operations are needed. If I choke those machines by generating an RSA key, essentially what happens is that my usual SLA that I have for response time from my other operations suddenly slows down significantly, and then I have a very big problem. I could define that process to have low priority, but that has other adverse effects. And now, in general, the amount of time it's going to take to generate a key becomes completely unknown. So although something really simple, it actually can be a problem in the type of solution that we're providing. And the last one, which is the most important for 3 main issues, is that of high bandwidth. One of the breakthroughs of this paper in Crypto 2018 was that it's okay to defer an honesty proof to the end and only prove it about the candidates actually accepted. All the candidates get thrown away, I don't care. And if someone cheated beforehand, then they maybe learned the RSA private key, but if I throw out that key, it doesn't do any damage. So I only need to do 1 proofing at the end, and that's very advantageous. So this proof is run once. It's not significant because it's only run once. And it turns out, though, that it requires uploading and downloading 170 megabytes per party. On a 100 gigabit per second network, that would take about 15 seconds, which is time, but it's okay. The problem is that we have a solution, which is a virtual smart card setting. I want to generate an RSA key between a laptop and a server, for example. And the laptop could be at someone's home, or it could be in a work office. And typical uploads can be between 1 megabit and 15 megabits per second. And that proof alone, just uploading the information, nothing else we do, would take 23 minutes in that setting, and probably even longer because you don't always have a stable connection. And that's before we count anything else. And that's, of course, just a huge problem. So it's actually essential to use a shorter proof like Ligero or variants that are more expensive to compute, but have much lower bandwidth, because just the upload time here is much, much too high. And there are other significant bandwidth savings, like we need private multiplication. In oblivious transfer, it's very fast. In Payer, it's much slower, but the Payer version is much better because it's much less dependent on the bandwidth that we have available. There are many other optimizations. I'm not going to go into them, but one of them that's just really important is that high variance is actually a problem. We probably prefer a protocol that takes 5 minutes on average and has low variance than a protocol that takes 3 minutes on average and has very high variance. Because applications don't necessarily work very well if it could take me 2 minutes or 20 minutes to get back an RSA key. Another thing that I want to point out is that often as cryptographers, we think that all the solutions have to be cryptographic. If it's running too long, then we have to make the protocol run faster. That's not always the case. So our implementation takes about 5 minutes from a weak home connection to a server. And there are engineering solutions to make that 5 minutes be fine, because in the virtual smart card case, we generate the RSA key upon installation, and it's like an antivirus installation, right? It runs in the background while you do other things. After 5 to 7 minutes or so, it'll tell you that it's finished, And it's anyway much faster than delivering a physical smart card. And
There's 2 minutes left, or 2 minutes?
2 minutes, okay. And in the server setting, we can generate many RSA keys and have them in reserve and then just provide them. They're always shared and refreshed, so it's proactive security, and then provide them whenever they're needed. And we don't actually have to generate them on demand if that's going to be a problem for the application. So these are very simple engineering solutions. I just want to mention that often complicated engineering solutions are actually less desired, like auto-detecting bandwidth and computing power is a problem because maybe there's big variance in what the customer is using, and now you've started to do something at a certain rate, and you again slow down and harm the rest of the system. So in conclusions, in non-SaaS settings, it's actually very hard to assume anything. There are big cost advantages to running on small and weak machines. You can have high bandwidth or low bandwidth. So we prefer to have our solutions actually work on very small, cheap machines only. Stability and predictability are often more important than speed. You don't want high variance. Not all solutions are cryptographic, and that smart engineering is also important in simple engineering. And I want to stress that this isn't a critique of academic papers. I think that academic papers need to push the science forward. But in reality, when you need to use these solutions, then often a very different balance is needed. And that does mean that there is room for academic research that looks at different balances. Often in an MPC paper, you want to have the fastest paper possible or the lowest bandwidth possible because you need to compare to others. And it's not a great sale if my paper is twice as slow as the fastest one and 1/10 of the bandwidth of the lowest bandwidth one. So it strikes a nice balance. Sort of people don't see that as something which is very attractive to sell. But in reality, these types of trade-offs are actually very, very important.
You're out of time.
Thank you.
Thanks for the great talk. We have one question posted on the chat channel. So question here is from Don Beaver about the flexibility of the cloud services. Don't the cloud services provide the elasticity you need to overcome things like RSA keygen taking over machines and preventing other responses? Or are cloud services just too coarse-grained or maybe unresponsive?
So firstly, not everyone is running this in the cloud. A lot of our customers are using it in the data centers as well as in the cloud. And in your own data center, often you don't have that elasticity. And elasticity isn't always that simple. Sometimes to achieve on such a very fine granular level on doing very local operations. And also there can be certain danger in if you're automatically cloning machines, then are you sure that you have strong separation between them? We have customers that are running between 2 different clouds. I'll have a key shared between Azure and AWS in the same region. So I have high bandwidth and everything. Elasticity between 2 different clouds is not something that we're going to really play around with. It's quite dangerous, if at all possible.
Great, that's the only question that's posted.
So there's a question in the chat, which is how fast can an ACD key pair be generated using your mobile server setting? I don't have that number on me. It's in the I think it's in the tens of milliseconds. I don't exactly remember, but it's not generating a key is not a very it's not an operation that you're doing at an extremely high rate. So it's not that important if it's 15 or 15 milliseconds, but I don't remember.
Okay. Thanks for that great talk. Next up is Omer Schlivitz, who's going to talk about the Diogenes paper and bringing that design to a production-ready state.
Hi. So this is a joint work with Bernardo, Justin, Dimitri, Mary, Hart, Claudio, Peter, and Riyad. And when I say work, I actually mean this is a joint review. So I want to scope what we've done and from that point to motivate our work. So there's a paper published last year called Diogenes. It solves or provides a solution for the joint RSA modules generation, same problem as Yehuda just described. And they also provide code, a lot of code, C++. And our job was to review this paper. So maybe the first point here is that it is a good opportunity for us to acknowledge the complexity and effort that it requires to actually build such a complex crypto system that is going to be used in production. And the other thing is that our review process was a bit unique. So we worked as a team. We were 9 reviewers. We've met with each other. We've met with the authors, and we needed to review the code and the paper and the security proofs. So this gives us kind of the second motivation here, which is maybe appreciating the differences between what is a review process for what we are used to in a peer review and what we might want to aim for in a production grade systems. So I'm going to briefly describe the problem of a joint RSA modules generation, then I will highlight some of the innovation in the Diogenes protocol. Then I will tell a few stories about the review process and would end with this attack that is probably the most severe attack that we found, that is also an educational attack, and then the insights. However, because this is a short talk, I would cheat a bit and start with the takeaways. Hopefully I will manage to get to the same slide at the end of the talk and maybe drive those points home. But just to mention those very briefly. So, and I'm putting the links for those that want to follow up and learn more. We are kind of open sourcing this process. So first is that optimizations requires proof of security. We usually, when we write papers, and then when we want to implement it in real life, we are making all sorts of optimizations. Now, even if they are trivial or make a lot of sense intuitively, the dog bite attack shows one example of how two very common and make sense optimizations combined together create this kind of attack. Second point is about the dialogue between cryptographers and developers. So we're in a good point of view to kind of see how this communication was made. And the angle that I'm trying to take here is about using some specification document as kind of a middle ground. So I would mention it later on. The next bullet is about a coordinator model, which is something specific to the Diogenes paper, but might be extended and used in other cryptographic protocols. However, it should be carefully defined. This is kind of, something which is an active relayer in a sense. So this is another thing. And the last point is the most obvious about reusing cryptography and also reusing code and writing code. I'm pointing it out, and we also wrote a note about it just because this is where most of the issues were found, right? Now, the problem is that we want to generate, a set of parties want to generate a biprime N, which is a product of 2 primes P and Q, and we want to generate it such that no party would be able to tell the prime factors P and Q. And this biprime is surprisingly useful. It is used, it can be used in secure computation protocols. It can be used to set up public parameters for some cryptographic primitives, such as verifiable delay function. And also, to give some examples, strong randomness, which is what brought us together, and also threshold DCDSA, just to name a few. Now, this is not a new problem. It's been around for 20 plus years, and correspondingly, there's been quite a lot of solutions for different settings to this problem, but you can describe all of them with a simple blueprint. And it's also very intuitive one, because at the end, we need to output a single biprime. So we only care about a single biprime, and it should be a multiplication of 2 random primes. So the inputs here is very simple to understand, just supposed to be randomness. So there is some setup phase because we do need to work with some encryption scheme. And then the game here is about generating the primes and then generating the biprimes in a secure way and testing them. And one easy way to think about it is, let's say we want to generate P and also Q, but for P, each party would take some of its randomness and would share it, and then we can add all of the randomness together to get this candidate. Then we need to do the best we can to test for primality, and then we can move on. Could be the byproduct, the biprime, and test it, and so on. So this kind of a funnel. Now, the requirements for Diogenes were very unique. One is that they needed a large-scale system, so 1,000 parties, which would made it one of the largest MPC to date. However, it should be very efficient in communication and also in running time, because it's going to work in real life. It's supposed to be secure against malicious adversaries. But also one interesting point is about the dishonest majority. So it's enough to have one honest party such that PMQ will not be revealed. Diogenes was published last year. It was accepted into a top-tier security conference upcoming, and they offer a few interesting ideas. So they are using this coordinator, which I would show visually how it looks like in a moment. But basically, this is kind of a party that is not part of the parties in the protocol, but it is doing a relay, but also an active relay. So it aggregates results and then share it to the parties. It allows to save in communication instead of doing n squared to communicate with all the parties. Parties work only with the coordinator. The encryption scheme used is based on ring LWE. It's additive homomorphic encryption scheme, threshold variant of it. There's the zero knowledge part. So you can basically run the protocol as a semi-honest protocol, and then only at the end for successful candidates, you need to generate this very big zero knowledge proof. And of course, it maintains high quality security. Now, visually explaining, so this is the blueprint. Now, just to give an example, each party communicates only with the coordinator. Then let's say share that we want to generate this prime factor. So each party would share its randomness, would send to the coordinator, it would aggregate it, and would send it back to the parties. As you can see at the end, there's this zero knowledge proof where a party can take only the successful candidates, compute a proof, send it to the coordinator, and then go offline. Then the coordinator can later on go and distribute it to verifiers. Okay, so finally I can describe a bit about the review process. Now, starting with some tools, and here I want to mention again the specification document. So we actually had two, one that goes from the paper to the code, and one that goes from the code to the paper. And this is important because if you think about it, when you write an academic paper, you usually try to optimize on writing the security proofs or making them as easy as possible, or the assumptions and so on. However, when you write code, you want to make it as efficient as possible. So those are not go hand in hand. And I would, in a moment, double click on this one particular specification to show what it looked like. In addition, we needed to use they use encryption, homomorphic encryption. So we need to use the tools for homomorphic encryption. It's funny because those are the same tools they used to build the protocol, but nevertheless, it needs to be tested. I'm mentioning cloud because we dynamically run the code. It's important, and it's hard to run a code that's supposed to simulate 1,000 parties, but it was very helpful. And GitHub to track issues, as I would show immediately. So specification doc, what?
2 minutes left.
1 minute, well, I'm not going to go anyway. So specification document is that includes the following. So there's the code flow, which means that there's a bunch of applications that needs to run, and we need to understand who is communicating with who and with what messages. However, eventually there's a cryptographic protocol, and within this cryptographic protocol, we need to understand the messages that goes from the clients to the parties to the coordinator. So for each round, we dissected it and kind of mentioned the parameters and the notations to bridge between the paper and the code. Now the pipeline, in case we found an issue, we had an internal discussion, we had a Telegram group, and we tried to figure out if there's what the root cause, if this is the real issue, some suggested solutions. We tracked and tagged this, and if anyone is interested in our tagging system, I'll be happy to share it, so ping me later. And then we do this kind of iteration with the authors. Finally, within, let's say, 2 weeks, we got to some revision. So this is maybe the best way to measure the output series by way of revisions. As you can see, it was impactful. Now, because I don't have much time left, I would not describe the dog bite attack. I would simply go over it by just mentioning that there is one optimization around the zero knowledge proof, one optimization around the packed ring LWE encryption that allows you to basically have enough equations to extract the K successful candidates for PMQ. And then a passive adversary can basically break the protocol. So just by looking at the public transcript, which is another part of the protocol of the Diogenes protocol that is visible to anyone, the attacker can just learn PMQ. So again, I'm going back to the insights and would open it for questions.
You're at time.
Yeah. I have more time?
No, you're at time. You're at your time limit. Any questions from anyone? I see one question posted on the channel, and that's from Mad. He's saying, backing out the details of this impressive work for a little while, why RSA and not class groups or genus 2 curves for an unknown order group if you need high assurance?
Yeah, that's a good question, and I asked it myself. Unfortunately, here the focus was, let's assume that this is the case, this is what we want, so it's out of scope for me to answer it properly. But there is a good good answer to this, and I would be happy to. I mean, it involves, like, you know, the economics of hardware and such. So I'll be happy to point you later on to the specific details of why.
Okay. Any other questions? I don't see any other questions on the Zulip side or on the Zoom side at the moment. Here's one. So that's not really a question for you. Okay, I think that's it for the talk. Thanks very much, Omer. Appreciate this. It's a very nice talk. So there's one more speaker in this session, and that's Rushab Pawar, who's going to describe a new, efficient, maliciously secure MPC platform for federated analytics.
Okay, sorry about that. I believe I'm audible now.
Yes, you are.
Okay. Hi, I'm Rushab, and this is joint work with my colleagues at Berkeley and VMware Research. So a large number of applications and services today can benefit from sharing their data with each other and running joint analytics on their collective data towards a mutually beneficial aim. And for instance, in the medical sector, such collaboration can enable healthcare institutions to perform better medical studies. And here's an example of one such analytical query expressed in SQL that we drew from the literature. This query aims to find the top 10 diseases contracted by patients who have been infected by a bacteria called C. diff. And in particular, the query can be expressed as a sequence of operations where first, all the parties combine their data sets together. They then filter out the rows where C. diff is true. These rows are then grouped together by the type of disease, and the size of each group is counted. And finally, the top 10 groups are identified after sorting them by their counts. Now, the problem in such collaborative scenarios, of course, is privacy. Organizations are often unwilling or unable to share the data with each other because the data may be highly confidential and they don't want to expose it to other parties. And there may even be laws and regulations that prevent them from sharing their data in the first place. Now, secure multi-party computation, or MPC, enables such scenarios without revealing the parties' data. The parties jointly run a cryptographic protocol that allows them to compute directly on encrypted data and only share encrypted data with each other. MPC protocols guarantee that no party learns any other information beyond the final result of the computation. And in more detail, the threat model for MPC and the security guarantees that we are interested in this work are as follows. Each party is allowed to provide its input of choice to the computation that they want to run. From the perspective of an honest party, the protocol should ensure that even if all other parties collude with each other, they should still not be able to learn any information about the honest party's data. And further, the security should hold even if the adversary is malicious. That is, it may deviate from the prescribed protocol in arbitrary ways. Now, state-of-the-art protocols for maliciously secure MPC work as follows. Suppose we want to run the SQL query shown on the slide that receives input from 4 parties, where party 1's data is first filtered using a select operation, and then all the parties' data is then joined together pairwise using a sequence of join operations. Existing MPC protocols require that the entire computation is first represented as a single large monolithic circuit, and then all the parties jointly evaluate each and every part of the circuit. So for instance, all 4 parties will participate in evaluating the select operation, even though it only processes party 1's data. But this monolithic execution is a far cry from how the query would be evaluated if security were not a concern. And for instance, this is how natural plain text computation of the query would work. The select operation would be run locally by party 1 without involving any other party. The next pair of joins would be run by the respective subsets of the parties and therefore could also proceed in parallel. And only the final join operation would involve all the parties. But existing MPC protocols are not able to work this way. They cannot take advantage of parallelism across parties. They can't benefit from offloading a part of the query circuit to local computation. And all parties must be involved in executing the entire circuit. All of this contributes towards the high performance overhead of these protocols, and the cost only grows with the size of the circuit and the number of parties involved in its execution. The question is, how can we decompose monolithic MPC so as to mimic plaintext execution? Because if we could do so, it would lead to significant gains in performance. Now, let's take the example of a strawman approach that mimics the execution plan of plaintext computation. The select operation in the strawman is executed locally as before, and each join operation is a separate MPC computation only involving the respective parties that provide input to the operation. The first problem is that each MPC subcomputation, by definition, reveals its output to the parties. For example, if party 4 is malicious, it obtains the output of the intermediate join operations MPC, which violates the security guarantee that we wanted, that only the final result of the overall computation be publicly revealed. Second, the adversary can provide invalid inputs to MPC subcomputations higher up in the plan. Even though MPC protocols allow each party to choose what input it provides, not all inputs may be valid for intermediate operations. For example, if a malicious party 1 executes the select operation incorrectly, it may try to input the results to the next join operation, even though the inputs might not have been possible had the select operation been executed correctly. And third, the adversary may attempt to provide inconsistent inputs to different MPC subcomputations. For example, in this case, party 3 is supposed to provide the same value x3 as input to 2 different join computations. But if party 3 is malicious, it may cheat by providing different values to the 2 joins. Now, these 3 problems are not an issue in monolithic execution and only arise when one attempts to decompose the computation. Our key contribution in Senet is the design of an MPC protocol that enables decomposed execution while overcoming these 3 challenges. Crucially, not all decompositions are valid, and the decomposition may be different than in the plaintext case. And our protocol formalizes the class of decompositions that are in fact valid. As a result, Senet significantly improves the performance of MPC execution while providing the same security guarantees in the presence of malicious adversaries. The parties can now offload some operations to local computation. The execution can be parallelized across parties, and each subcomputation only requires the necessary subset of parties, which reduces execution cost. Overall, our system makes the following contributions. Senet's MPC decomposition protocol lies at the heart of the system and formalizes several ideas and develops new techniques to achieve its goals. The protocol is general purpose and may have applications beyond Senet and SQL-based analytics, though it is particularly well suited for the latter. We then turn to the matter of designing efficient circuit representations for SQL operations. In particular, we develop a small set of efficient circuit primitives and then show how to express higher level SQL operations as a composition of these primitives. Finally, we put the above pieces together and show how to execute analytical SQL queries using Senet. To do so, we develop new query planning algorithms that determine how to decompose the query circuits and execute them using Senet's MPC protocol. In particular, we develop a cost model for our protocol, and the query planner uses this cost model to identify the optimal decomposition. I will now give you a closer look at how we develop our protocol. For the other aspects of the overall system, I would encourage you to read our paper, which is available online. So to understand the steps that we take to develop our protocol, let's start with the strawman MPC decomposition that mimics plaintext execution. The first challenge that we needed to overcome was we wanted to ensure that intermediate MPC computations do not reveal the output to the parties. To prevent this leakage, we develop a technique that stitches 2 different MPCs together. This approach is called soldering. The soldering protocol securely transfers the output of one subcomputation to the next without decrypting it.
Rajan, 2 minutes.
Importantly, yes. Importantly, our soldering protocol is very lightweight and works even when the parties in the first circuit is a subset of the second. The second challenge was to ensure that the adversary is not able to provide invalid inputs. This means that given a subcomputation, we need to be able to deduce what possible outputs are valid. And then the parent MPC must be able to efficiently verify that the received inputs belong to the range of possible values. This verification is only possible if each subcomputation can be efficiently inverted. And we say that a particular decomposition is admissible only if every subcomputation is efficiently invertible. Finally, if a party provides the same input to two different subcomputations, we need to make sure the inputs are consistent. And for this purpose, we limit the admissible decompositions to tree structures alone and not graphs. Now, let me give you a glimpse at how Senet improves the performance of MPC compared to monolithic circuit execution. So we evaluated the performance of Senet on the TPCH benchmark, which is an industry standard benchmark for SQL analytics that consists of 22 complex queries on data across 8 tables. And in our experiments, we assumed that each party held a single table. We compared the performance of Senet against a baseline implementation of the state-of-the-art WRK protocol for monolithic MPC execution, as implemented by the AG-MPC framework. And this plot shows how the performance gain offered by Senet against the baseline. We find that Senet can support 13 out of the 22 queries, which shows its expressiveness. And importantly, Senet is up to 145 times faster, bringing MPC deployments for analytics that much closer to being a reality. So in summary, Senet is a platform that enables collaborative execution of SQL-based analytics, even in the presence of malicious adversaries. It is up to 145 times faster than the state of the art by combining a novel protocol for MPC decomposition with efficient query planning algorithms based on a cost model. With that, I will conclude and thank you for your attention. I'm happy to take questions now.
Thank you. So I don't see any questions at the moment posted on the Zulip side or on the Zoom side. We'll wait a minute here just to make sure nobody's posting at the moment.
There's a thing on the chat, which is there an implementation?
Implementation, yes.
Oh, yes, there is an implementation. So we designed and implemented the system and evaluated it.
And a related question is, how many parties are used by Senet, and what is the trust model you enforce?
So the number of parties that can use Senet are variable, as many parties as required. We have experimented with up to 16 parties. And the threat model is that we want to protect against malicious adversaries in the presence of a dishonest majority.
Okay. Now, a question on the Zulip side from Eduardo Soria Vasquez. He says, are you dealing only with full threshold adversaries? Otherwise, how do you deal with the relation between the adversary structure and the party parallelism structure?
I'm sorry, could you repeat the question, please?
Sure. Are you dealing only with full threshold adversaries? Otherwise, how do you deal with the relation between adversary structure and party parallelism structure?
I'm not entirely sure what the question means, so maybe we could take this offline.
Yeah, let's take that one offline because I'm not exactly sure what that question means either. Another question from Jonathan Hoyland: how do you ensure that decompositions are valid? For example, what's the mathematical framework you use to define valid versus invalid?
Right. So so for a valid decomposition, we require that each subcomputation that is not the root is efficiently invertible, which means that it should be easy to find a possible set of inputs given an output that the subcomputation produces. And as a result, we can embed a verification check in the parent circuit that the subcomputation feeds into. So invertibility is the key requirement here.
Okay. I think that is all the questions posted, and we are close on out of time here. So thank you for a great talk.
Thank you.
With that, that concludes session number 3, MPC for RWC 2021, and concludes the formal sessions for today. Please feel free to continue using the Zulip channel for this session to continue discussions. And please come join the social hour that starts just about now.
Yeah, start. We're going to go.